So these properties are best seen through suitable example functions that show exactly what we're talking about. So let's consider the following example function. And we'll just consider a function in 2D. Specifically, we'll consider the function phi of r, where in Cartesian coordinates the position vector will be given by x, y is equal to x times y times e to the negative x squared plus y squared. The gradient of this function can be readily evaluated by first taking both partial derivatives. The x partial derivative of this function is going to be y times 1 e to the negative x squared plus y squared plus x times e to the negative x squared plus y squared times negative 2x. Or simplified, d phi dx is going to be y times e to the negative x squared plus y squared times 1 minus 2x squared. The y partial derivative of this function is going to be calculated similarly, and we'll end up getting that d phi dy, the y partial derivative of this function, will be x times 1 minus 2y squared times e to the negative x squared plus y squared. So the gradient vector for this function, the gradient of this function phi, is the vector x times 1 minus 2y squared times e to the negative x squared plus y squared. It's the x component, and the y component is 1 minus 2. The x component is y times 1 minus 2x squared, and the y component is x times 1 minus 2y squared times e to the negative x squared plus y squared. And we can even simplify this a little bit if you want to just write this as e to the negative x squared plus y squared times the vector y 1 minus 2x squared x 1 minus 2y squared. And using my Python code, we can see very clearly that this is a plot of the function in 3D, where the z coordinate is the value of the function, and you have two peaks of this function and two valleys of this function. But the general behavior of the function we can just visualize strictly in the domain using a density plot, or what's called a level curve plot. So if we sort of pick various values of the z coordinate, the value of the function, the behavior of this function can be strictly visualized down here in the xy plane, and just in the domain of the function. And this is a common idea in visualizing functions of 2 variables and of 3 variables. Definitely of visualizing functions of 3 variables, we're almost forced to use this concept of level sets. But you can clearly see that this is what this function looks like if we plot this function out. And if we restrict ourselves to the density plot or the level curve plot of this function, we see very clearly what we were talking about before, which is exactly that the value of this function is changing very, very specifically with respect to the domain, with regards to the domain. And specifically what's plotted here in each one of these plots is the behavior of the function as well as the gradient vector field. And you see that the gradient vector at each one of these points, if you evaluate the gradient vector, it's pointing in the direction of fastest increase at each one of these points. And it's directly characterizing the behavior of this scalar function. So if this is, say, a given temperature field, the gradient is always pointing in the direction of fastest increase of temperature at any given point. These arrows are the gradient vector that we just calculated, we just computed at each one of these points. Well, what's also interesting to note is that if we consider the level curves of this function, the gradient vector is always going to be perpendicular to the level curves. So the third property that we talked about before, the gradient vector, or the directional derivative in the direction perpendicular to the gradient vector is always 0. You should clearly see why. If you, at any one of these points, take the directional derivative in the direction perpendicular to the gradient vector, you're taking the directional derivative along a contour curve of the function, or along a level curve of the function, and the function is constant along these level curves. So for instance, for the level curve of the value 1, this is the level curve corresponding to the value 1. And if you were to take the directional derivative along that level curve, the function's value is staying constant. So the directional derivative, it makes sense, should be 0 along those level curves. So a good exercise would be to show that this is true for all functions. So consider a scalar function f, or a scalar function phi of r. How can we show that the gradient vector is perpendicular to the level curves of the function phi? And the main idea here is that in 2D, a level curve of a scalar function phi is equal to some constant d, and any level curve can be parameterized as r of s, say, is equal to x of s and y of s. So on this level curve, phi of x of s, comma y of s is going to be equal to the constant value d. And if we differentiate both sides of this equation with respect to s, and we also have to differentiate the right-hand side. And let's make this a capital D to denote that it's the constant level d. Well, the derivative of this composition of functions is just d phi dx times dx ds plus d phi dy times dy ds from the multivariable chain rule. And the s derivative of a constant is equal to 0. So what this is saying is that the gradient vector of the scalar function phi dot product with the vector r prime, or the velocity vector, which is tangent to the curve, is equal to 0, which means that the gradient vector is perpendicular to the tangent vector along the curve. And there you have it. This proves that if you have a level curve of some function, so say this is the level curve phi of x, y is equal to d, at any point along the curve, the gradient vector will be pointing perpendicular to that curve, because tangent to the curve is the vector r prime, the tangent vector to that curve. And this directly matches up with what we're seeing in that picture. Now, a useful exercise for you to do at home would be to show that this also holds for level surfaces. So this is what I've just done is I've shown that this is true. The gradient vector in 2D for a scalar function of two variables is always perpendicular to the level curves of that function. It'd be useful for you to show this also in 3D. That if you have a function of three variables, x, y, and z, that the gradient vector of the function phi is always perpendicular to the level surface, or the level surfaces of the curve. So the idea would be that you consider a specific level surface at D and show that the gradient vector will always be perpendicular to the level surfaces of that function of three variables. The main idea and the main thing that we've kind of shown here is that for any scalar function, or scalar field, the gradient vector determines all of the information needed to evaluate the rate of change for the scalar field. So the performance of the function phi and its local behavior is completely determined by the knowledge of the gradient vector of that scalar field. Now, it turns out that vector fields are going to be a little bit more complicated, and understanding vector fields is going to be a little bit more complicated. But it turns out that we have a special name for a vector field that can be expressed as the gradient of a scalar field. Given a vector field F, if there exists a scalar field phi such that F is equal to the gradient of the function phi, then we say that F is a conservative vector field. With potential function phi. F is also sometimes called a gradient vector field. This is a definition of a conservative vector field. Or a gradient field. And these fields are these types of vector fields are very, very important in physics. Everywhere from, gravity, so gravitation, to basic electromagnetics. So electromagnetic fields, in some sense, can be viewed as conservative vector fields with the existence of a potential function. So this is saying, in terms of equations, that in Cartesian coordinates, if F is conservative, then the first component of F is given by the x partial derivative of phi for some phi. The y component of the vector field F is given by the y partial derivative of some potential function phi. And in 3D, that the z component of the vector field is also given by the z partial derivative of some potential function phi. Now, a little bit later on, we'll get into exact conditions for what guarantee and why they guarantee that a vector field is conservative in a given region. But it is important to point out that not all vector fields are conservative vector fields. I'll give you a very simple example right now. The vector field determined by the cross product of omega with r. We'll say omega is a constant vector. Is not conservative. This is, in Cartesian coordinates, the same thing as f being equal to the cross product of omega 1, omega 2, omega 3, x, y, and z or the vector field omega 2z minus omega 3 times y negative omega 1 times z minus omega 3 times x for the y component, and omega 1 times y minus omega 3 times x. So if this is our vector field P, Q, and R, this vector field is not conservative. And we'll see why, exactly why, and this condition is not conservative vector field in a little bit. But that the main idea here stems from the fact that if you take the y derivative of P, you get negative omega 3, and if you take the x derivative of Q, you get positive omega 3. So dp dy minus dq dx is equal to negative omega 3 minus omega 3, or negative 2 times omega 3, which is non-zero. So a constant non-zero vector. So this is actually giving us exactly that this vector field is not a conservative vector field. And it turns out that this will be, in general, a useful test for us to test if a vector field is conservative. And I'll summarize that above this example, just so that you have it in your notes. That one of the useful tests that we can check very, very quickly and kind of see whether or not a vector field is conservative is to look at the following three things. We look at dp dx minus dq dx, or dq dy, or dp dy minus dq dx, for any conservative vector field. This has to be equal 0. We also have to have that for any conservative vector field in 3D, dq dx minus dr dy has to equal 0, and dr dx minus dp dz has to be equal to 0. So any conservative field f must satisfy all three of these relations. And we'll see exactly why a little bit later on. This condition is going to involve the idea of the curl of a vector field, which is one of the more advanced ways of taking the derivative or evaluating the rate of change of a vector field. We talked before about how vector fields are more complicated than scalar fields themselves. But it turns out that for a given vector field, if it's conservative, has to satisfy these three relations, these three relationships, and we'll see why a little bit later on